Alright, welcome back to Mr. PL's with Algebra 2, Unit 1, Topic 3, SLT16. Perfect warm-up for reviewing what we had done in the last video, which is trying to take 2 points and find an exponential equation out of it. So it says you started the experiment with 2,000 bacteria. So that means after 0 hours, we're going to make X represent the amount of hours and Y represent the amount of bacteria. So that's 0 to 1,000. Okay, so use a parenthesis for that. So it's 0, 2,000. And after 1 hour later, it's 2880. Now, from the last video, we're going to set the answer equal to y. So 2880 is equal to starting point times the rate, which is, in this case, b, to the first power. And then the other one was 2000 equals a times b to the 0th power, which is right there. Okay, so basically the x is becoming the exponent of the rate, and the y is the answer. So 2880, so I got to use my calculator. 2880 on 2880 divided by 2000, which is going to give me a decimal of 1.44. So 1.44 equals, a's cancel because 1 minus 1 is 0, and b minus 1 is just b. So b is 1.44. Now, I don't need to solve for the y-intercept because it's right there. So that's the starting point, which was at 2000. So the equation is y equals 2000, which is the starting point, times 1.44 to the power of x, or t amount of hours. How can we change the model to represent this bacteria per minute? Okay, so that's what this video is about. It's about changing, in this case, hours to minutes, or changing any one rate to something else. Now, if I want to change this to minutes, there are 60 minutes in an hour. So I'm going to change the rate to 1.44 to the 60/60ths. Now, 60 divided by 60 is still 1. So basically, I have not changed the value of anything. So I'm going to change the x to a t. That doesn't really matter because I can use any, I'm going to call it f of t. So I'm going to go to function notation now. Equals 2000 times 1.44 to the 60/60ths. Now, I want to change this rate to 1 minute. So I want to change this to 1/60th. But if I do that, then I need to take the 60 on top and move it to the outside. So it's going to become 1.44 to the 1/60th power to the 60t power on the outside. Now, the reason why this is the same is because when you have an exponent raised to another exponent, you multiply the exponent. So I really still have not changed anything. 60 times 1/60th would be 60/60ths, and 60/60ths is the same as 1 whole. So that's the reason why this equation, this equation, and this equation are all the exact same thing. Now I've almost changed my rate to minutes. I need to now do 1.44 to the 1/60th. Now I gotta put that in parentheses, 1 divided by 60 to make sure it does that first. And enter, and I'm gonna round that to the nearest thousandth. So that is about 1.006. That's gonna be close enough. So that's to the 60t power. And there's your equation. Alright, so basically all I did was change this, 1.44, I raised it to the 1/60th power, and I simplified that, and I got about, it's actually 1.0060959. Now, if I want to keep more significant digits, I could have kept the 609. Alright, so that's basically what this video is about. So I just did an example of that. That was the first question. That's right here. I already did that. So this is the formula for finding growth. So you start with the starting point times 1 plus the rate, which is what I did earlier, to the t power. So that's exponential growth. Now, this is the formula for compounds. So this is exponential growth, but it's compounded, which means you're getting interest on your interest in this case. So that's why you're using n. N represents the amount of times it's being compounded. That'll be in the next video more, though. So you're basically seeing where that formula comes from in this video. So I want to change this one from weeks into per day. So if t is the number of weeks, and there are 7 days in a week, so I'm going to change this to 1.2 to the 7/7ths. Now, in this case, I'm just going to go straight to the answers. I know you've already seen me do an example, so I'm going to go to the 1/7th and 7t on the outside. Now, 7 times 1/7 is 7/7. That's the reason why I use 7/7, because there's 7 days per week. So it's always important that you look to see what are you converting. I'm converting weeks into days. So this will always be 1 over however many there are, and then use that same number on the outside. And 7 was on the outside, so that's Q of t is equal to starting point times rate. Okay, so now all I got to do is simplify that rate. So 1.2 to the 1/7 power, 1 divided by 7, and parenthesis, and that changes it to about 1.0263. 0263, now that's an estimate to the 7t power. Now, notice that we're going to raise this to the power of 7 times more. So yes, we're making the rate much, much smaller because we're making the rate represent the amount of growth per day. So it's going to be growing for 7 times more days than it would be weeks. So that's the reason why the rate is being made so much smaller, because you don't, if it's going to be doubling per week, then it's not going to be doubling per day. It's going to be doing less than doubling. So that's why you're doing it to the 1/7 power to represent how much it's going to be doubling, or not doubling, but increasing by, multiplied by, in order to get to the same amount at the end of the week. The list price of the new car is $22,000, a decrease of the value of the car by 10%. Write a model for the value of the car is, okay, so that's $22,000 times 1 plus the rate, which is 0.1, it's not compounded, to the power of x, or t in this case. Doesn't really matter. How can we change to represent loss per day? Okay, so this was per year, so that would be 1 plus, whoops, so that'd be 1 plus 0.1 to the 1/365th to the 3/65th x. Okay, just like I did before. Alright, so I think I've covered that. So let's get to exponential growth versus decay. Now, I think I talked about this in the last video. Anything that's growth means that the rate is greater than 1. That's growth. If it's less than 1, it's decay, which means it's getting smaller. So anytime you multiply by a fraction, a proper fraction, it's going to be getting smaller. So this is growth. This is decay, because this is less than 1. Whatever the y-intercept does not matter. The only thing that matters is the rate. So in this case, it's 0.93, which is 7% decay. So maybe I want to talk about, so I know it's going to be in a future video. This is a 23% growth. This is a 45% decay. Why do I know that? Because this is 45 hundredths less than 1. This is a 7% decay. That's 7 hundredths less than 1. This is a 63% growth, because that's 1.63. That's 63 hundredths more than 1. And this is a 103% growth, because 2.03 minus the 1, that's usually the rate, 1 plus the rate. So the growth rate in this case would be 103%. And this one's going to be a decay of 32%. Because that's how much less than 1 it is. Okay, so that's very much the same as what I just did right up here. I did this earlier in the video, so I don't need to do that again. In 2000, Chelsea's grandmother left her a penny worth $3,000. Okay, so we need to set our x and set our y. We're going to let x represent the amount of decades, because that's what it says right here. And we're going to let y represent the amount of total value of the painting. So in this case, so it's going to be a, I would first have to find the rate, because it looks like they only gave us a starting point and then a later value. So 03,000, and 2010 would be 1 decade later. It was 3150. So the first thing I need to do is find the rate. So 3150 equals a times b to the first power divided by 300 equals a times b to the 0th power. So it looks like 3150 divided by 300 gives us 10.5. So it looks like b is going to be 10.5. So I don't remember that number. Did I mess it up? That was 3,000. Okay, that makes more sense. So it's 3150 divided by 3,000. And that's going to give you 1.05. Yes, that is the right amount. So B is 1.05. So now we know the rate is 1.05 to the power of x. Now if I want to change that to every year, then I would just do this to the 1/10th power to the 10x, just like we had done before. Alright, skipping through these, getting to the homework. Ned opens a savings account with an interest rate of 2% per year. His initial deposit is $500. Rate an exponential model representing the amount into his savings account. So it's not compounded, so we can just simply use growth. So that's $500 times 1 plus the rate. The rate is 2%, which is 2% increase right there, to the x power. All right, so there's our model. How can we change the model to show the amount of savings each day? All right, so if this model represents per year and we want to change it to per day, there's 365 days per year. So 2% growth is going to decrease significantly. So that's 500 times 1.02 to the 1/365th. That's going to give us a really small decimal, to the 365 times per year. Okay, so calculator, 1.02 to the 1/365th is 1.0000. Okay, so 1, 2, 3, 4 zeros. So this changes to 1.0000543. So I'm going to round that to the nearest 3 significant digits. All right, to the 365th x, and your initial amount of money was $500. All right, so there is your number. Yes, that is a very, very, very minuscule amount of interest that you're multiplying it by each day. You're not changing much. That's really like multiplying by 1, but it's a very, 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 very small amount more than 1. So you're not getting much interest per day, especially when it's only 2% interest to begin with. All right, thanks again for watching. If I helped you learn something about compound interest, please give it a like and subscribe if you haven't done so already.